この computer に okay.
Oh yeah.
Okay. Okay, I'll start now. So basically, you can understand the logic circuit. You can just forget about how this thing would formulate a circuit because it's only about logic. So first, let's say, so this typical logic gates suggests that when there are two inputs, one of them is x1 and one of them and the other is x2. When they are attributed with different truth values. Yeah, when they are with different truth values, how this different expressions, this different expressions here would give you different outputs of truth values, and that's how this whole table works. So from the beginning here, the first line here, it says that, so this is a case when, actually you should look at it as like that. So this first case is that when x1 is false and x2 is also false, that's when their truth values are both 0. And this is when x1 is false and x2 is true. So in this case, x1's truth value is 0 and x2's truth value is 1. And so on. You can just tell how they work.
Okay, okay. This is like the first time I'm understanding that.
Oh yeah. I was like a bit lost because he didn't really explain that from the beginning. So you have to because I learned all those logic things when I was doing my undergrad. So I had to figure out how the table works at the beginning, but he didn't really explain that. And so yes, that's how this whole thing suggests here. And there is no difference from this first column and this third column. There are just different ways to express the function. So you can just ignore all this because that's how you have to write it when you are writing it in a mathematical way. But in like typical logical, logic expression, you just write it like that.
Okay.
Yeah, and that's the thing.
And what is XOR?
Oh, okay, I'll go through that later.
Oh, okay. Sorry. Okay.
Yeah. So it begins with when we just want a false output. That's when we want a 0 output, and that's when everything is 0, obviously. And this thing here, it means x and it means and something. That means when the two outputs needs to be like the same in order to get the final truth value as 1. In, let's say if x1 is false and x2 is false, then x1 and x2 would obviously be false. And actually the only situation when x1 and x2 would be true is when both x1 and x2 are true. So that's when we have here, you can see that in this column, x1 and x2 are both true. So they are both 1 and the output will be 1. So the output is 1 only means that it's true according to this logic gates.
Okay.
Yeah, I wish I explained that clear.
Okay.
Yeah, and I think for now we can just ignore that because I think it's more related to the thingy down here. So we can just yeah. And here is when you want, so if we only have one, if we only have an input x1, then obviously the output is true when x1 itself is true. So here we can see that when x1 is 0, it is 0, and when x1 is 1, it is 1. So that's how it works. And same for x2. Yeah. And XOR means, so I think I should first explain what is OR. OR means that X1 or X2. So if we want, say, we want this thing to be true, then obviously it should be true when one of them is true. Meaning that if X1 and if both X1 and X2 are false, meaning that their truth value are both 0, then the output is 0, like here. Here it is 0.
Oh.
And in other cases, we can see that here X2 is true, and here X1 is true, and here both X1 and X2 are true. So in this case, it's both the OR function here, we can get a true output. We can get an output.
Okay. Oh my God. Okay. I'm like having a light bulb moment. Okay.
Okay. And XOR here means that so it's like they have to, it's like making X1 and X2 to be mutual exclusive, meaning that we can only have one of them to be true in order for XOR X1, X2 to be true. So if both X1 and X2 are true, in that case, they are not the same. So it's not an exclusively one of them to be true. And in that case, it is false. That's how you understand that. So we can see that here still, if X1 is false, X2 is true, we get a true output. Oh, sorry, not this one, this one. And here, if X1 is true, but X2 is false, then we get a true output still. But when both of them are true, in that case, XOR X1, X2 is false, because we want them, only one of them to be true. And that's how it works. Yeah. And and this thing, I think it means neither nor.
Okay.
So obviously, it's neither nor. It's only true when both X1 and X2 are false. So we can see that only here it is 1, and here they are all zeros. Yeah. And EQ means, I think it means equal. So this thing is true when X1 and X2 have the same truth value. So when both X1 and X2 are true, or both X1 and X2 are false, we get a true output for this function. So we can see that here is 0, 0, so here is 1, and here is not the same number. So here they are both 0, and here is 1, 1, and so here is 1. Yeah.
Okay.
Yeah. And here now, this not means negation. So obviously it is true when X2 is false. So you can see that it's the opposite to X2's truth value here. Here it's the opposite, and same for X1. And neither and is when no, sorry, it's not neither and, it's not and. So it's the opposite. It's the opposite of and. These two are opposite. You can understand it as a negation for this and function. So it's the you get the opposite truth value from this. So it's only true when both X1 and X2 are true. So it's only false when both X1 and X2 are true. Sorry, yeah. That's how this very basic thing works. And in logic, usually this thing is called truth functional logic, I think. Truth functional. Yeah, that's the formal name for this whole system, and it's quite simple. Yeah, and here we get these thingies and all these things. They are just different ways to write what I have just explained about. Yeah, so here we can see that. So here we don't have some X1, X2. We just attach the different numbers. I mean, a 0 or 1 in them, because 0 and 1 suggest different truth values. So not 0 is obviously 1, and not 1 is 0. So that's the expression for this not function, the negation function. And here this and is something the same. So it's only true when both because we can just understand the thingy in the bracket as x1 and x2, only this time they are just directly written with their truth values. So still, when both x1 and x2 have truth value 1, the output is 1 for this AND function.
Okay.
Yeah, and same for this OR thingy here.
Okay.
Yeah. And sorry, I think this whole sentence also caused some confusion. I think what he meant by saying, by combining the aforementioned 3 logic gates only, any transform for any number of inputs can be realized. So I think what he means is that these 3 different expressions, these 3 functions, not, and or, only by using these 3 different functions, we can basically achieve any like normal, ordinary arithmetics. It's like he just wants to say that these 3 functions are complete, so they can form a complete set to express basically everything in this simple calculation system. So that's what he wants to express here. And here are some examples, I think. Yeah, let me just go through that. Yeah, so because in computer like language, usually we just use binary systems. And since we have in this truth functional logic gates, we attach 1 and 0 to suggest truth values. We can just interpret the truth values as numbers of 0 and 1, and then we can just combine the functions with the truth values and to just formulate some different expressions in order to represent the binary calculations. And I think that's what he means. And here are just examples of how you actually use binary system calculation to just express everything this 3 logic gates can express. Yeah, and here we can just start from here. So this S bracket for a position number means that, so when doing binary calculations, let's say we can have 1 0 plus 1, and we can get 1 1, and in normal system is 3, and this is 2, and this is 1, right? So here the position number is this number. So this number on this position. Yeah.
Okay.
And the carry is when there is a, so sorry, I think this is not a very good example. So if we have 1 1 plus 1 in binary systems, we should have like that. Because when we reach 2, we need to move to the next position, right?
Okay.
So that's what a carry means. So a carry means when you have to move to the next position. And that means it basically means that you have to add a digit. Yeah, you can just understand it as that, I think. Yeah. And here is quite obvious because we can just see the example here. So this S00 equals 0. It means that when adding 0 and 0, obviously we get a 0 for position number. Meaning the say, if it's a 2-digit number, it means the number here is 0. And if it's 0 1, we still get a position number 0. We get a position number 1 because it's 0 plus 1, right? It's 1. And if it's 1, 0, still it's 1 because it's 1 plus 0. But when it's 1, 1, because it's 1 plus 1, in binary calculation, it's 1. Here is 1. Sorry, here is 0. So we get a 0. Yeah, that's the calculation system for position numbers. But for carry numbers, meaning the number here, we need to use the C function, which is C00 is 0, C01 is 0, C10 is 0, because in this cases, they are just one digit thingy, and there is no thing. We don't need to add another digit because we haven't reached the number 2 when doing summation. But when it's 1, 1, we add another digit. So in the case of 1, 1, it becomes 1. So here is 1. Yeah.
Okay.
That's how we operate the calculation system in binary system. But what I think maybe the computer scientists have discovered is that they found out that actually this kind of expressions are just resembling some sort of calculation in the previously introduced logical system. So what they discover is that C is the same as AND, because we can see that here, the calculation here is just the same as the AND function. When we attach like the same truth value to AND function, we get the exact same kind of output. So they're just the same. And when we are, but in case of S, it looks like OR, like here suggests, but it's actually different because when it's X, when it's S11, if it's OR 11, sorry, my nasty handwriting. If it's 411, it's still 1. But in the case of S system, because it's a position number, if it's 11, we need to move on to the next position. So it becomes 0. So in this case, they are just different. So it's not OR, and it's actually the same as XOR. So it's exclusive OR, like the thingy here. This thing. Yeah. Let me choose another color. Yeah. So sorry, let me just go over it again. So if we understand it's as XOR, we can see that if it's 0, 0, we get 0, because XOR means that one of X1, X2 is true, but they can't be true at the same time. Yeah. So when they are true at the same time, meaning that if it's XOR 1, 1, it's 0 because they are true at the same time. We get a false output. We only want a true. We only want one of them to be true, but the other one is not true. So that calculation represents the S system just the same way as how AND function represent the C function here. So that's what they discovered, and maybe they just formed some sort of circuit using the thingy here, and I think maybe that's how they actually form those circuits in the physical world when they first invented the computer machine thingy. That's how they
I have a question.
Yeah.
The S for a position number and C for a carry, is that a random like rule that they came up with, or is that always true? Like, do we always use S for position numbers and C for a carry, or is it just for this example?
I don't know actually, but I think maybe it's like a conventional thing, because if it's not conventional, I don't think the professor would choose such an expression. So
yeah, that's why I was confused. Like, where did it come from?
Yeah, I don't know either.
Okay.
But I think maybe it's conventional because
Okay.
yeah, usually they just use some, if there is a convention, they just follow the convention, right?
Okay.
Yeah.
And then
But-
for the first page,
Yep.
the rows with the blanks, like on X1 and X2
X1.
on
Oh,
the
here.
table.
Oh, I
Yeah,
think
what
they
do
just
those mean?
suggest some like very different occasion when we get those different outputs, but I don't think it's very relevant here
Okay.
and now. So maybe we can just ignore that, but we can just you can get some reference from the thing on the right column. So those are different occasions when you have also need to consider the other input. So in this case, even though it's x1, if you also add x2 into the consideration, sorry, how to say this, the output would shift a little bit. But yeah, but I personally don't find them very relevant with
Okay.
what we will do later. So I
Okay.
did think through them yesterday because I found them quite confusing and I thought them through, but I didn't put on a note, and it turned out they are not so relevant, so I just forgot.
Okay.
Yeah,
Okay.
sorry.
No, it's okay.
Um,
Thanks.
Okay. So maybe next we can just
Yeah.
see this thing. So here, this expression just means that you can actually express the XOR function by using OR function, AND function, and NOT function. So it means that these two things are the same. So it means that if you attach some truth value to this x and this y, and the same truth value for the x and y here, we get the thingy on the left side and on the right side the same output every time. So these two expressions are equivalent. That's what he is suggesting. Okay. And here we can see that they are equivalent. Yeah, but you can just read it through. So x or xy means that or this thing, whole thing in the bracket, that means and x not y. So
okay. It's like math.
Yeah,
okay.
and this thing and this thing, or this thing or this thing.
Yeah. Okay.
That's how it means. Yeah.
Okay.
So this thing is S. Oh, sorry, it is S, right? Yeah, this thing is S. Yeah, because it's XOR, so it's S. And so we can just carry on. And here they are just, here it suggests a situation when there are three outputs. Yeah, because previously here we have two outputs. But in actual normal cases, we can get tons of different inputs. Sorry, not outputs, inputs. And here is an example when there are three inputs, meaning that we have three different things and we need to do a calculation between them. And that's how the position number works here by suggested by this SF. And that's how the carry number works. Yeah.
So this is just the same logic as before, except there's three inputs.
Yeah, it's the same logic, but we can just go through them and just briefly introduce them. So this thing means that when we are adding 0, 0, 0 together, obviously you can see that if we add 0, 0 plus 0 plus 0, it's just 0. So it's 0 on both SF and CF, on the position number and on the carry number. And here, if it's 0, 1, 0 adding together, we get 0. So it's SF So on the position number it's 0 and there's no carry, so it's 0. And same for 100 and 001. So we won't go through them. But if it's
Okay.
110, 1 plus 1 in the binary system is 10, right? So for position number, it will be 0 because we don't have anything on the digit.
Okay, right.
So it's 0.
Yes.
And on carry number, because it's 1 plus 1, we have another entry for another digit. So it's 0 here. So CF is 1.
Okay.
And for 001, it's the same. And 101 is also the same because in summation, for something plus something, the order doesn't matter. And when there are 3 entries are both 1, that means 1 plus 1 plus 1, we get 1, 1 in the binary system. So we can see that it's like that. Yeah.
Okay. For the one below the first green underline, the SF001.
Yep.
Equals 1. And why is CF 0?
Because it's 0 plus 0 plus 1. So it's still 1. The order doesn't matter, actually.
Yeah. But for CF, why is it 0?
Because there's no entry. You see, if it's 0 plus 0 plus 1, then we get the output is 1. 0 plus 0 plus 1 is 1. So there's no number on this. There's no number on this.
Oh, okay.
Yeah.
Okay.
That's the carry. The carry is.
Right. I forgot that was what the carry was.
But you're adding another position. Yeah.
Right. Okay. Okay. Thanks.
So here comes the explanation saying that actually, if the carry is 0, SF something 0, it's just equal to S something. So that's that's when, say, in this case here, if the carry is 0, so CF equals 0, that's when the carry is 0, and SF 010 is just equal to S 01. That's how it means.
Okay.
Yeah.
Okay.
But actually, this whole SF and CF system is not 100% the same as this SC system, because we now have 3 different we now have 3 inputs instead of 2. So actually, its logical expression will shift a little bit. So that's so in this writing system, we just differentiate them into 2 different cases. And the first case is when the carry is 0, because it's binary system. We only have 2 different outputs, either 0 or either 1, right? So they just divide it up to 2 different cases. And when this is the first case is when, like I said, when the carry is 0, we can just understand the SF system as such. But when the carry is 1, it should be further generalized. When the carry is 1, SFXYC equals to S bracket SXY dot C, comma C, and CFXYC equals to OR bracket C, XY, C, SXY, and C. So that's just a way to just, if you write it as such, you can just avoid introducing too much other, expressions for indicating what the calculation system is about. So I think in some very old computing systems, that's how they have to just write SF, define SF and CF very fully into this very basic terms.
Right.
Yeah, in order for
So you can see how like if there are three inputs, you can view it as a bunch of like combinations of two inputs going in.
Yeah.
Okay.
That's how it works.
Okay.
Yeah.
Okay. I kind of understand.
Yeah. And so here, this this whole document is so messy. Actually, what he means by now is just and or not has completeness, like I just said, like it also has said here. By combining the three logic gates, only any transform for any number of inputs can be realized. And actually, these are just examples for showing that you can actually do that. And that's I think in logic terms, so this system of having and or not functions, this system has completeness. So it's a complete system for expressing just very basic calculation.
So it's like all you need. You don't need anything else.
Yeah, exactly. Okay. But actually there is another even stronger logic gate, which is not and. And so briefly speaking, since we have proved that and or not have completeness, if we can find any other expression which can express just the same as this three logic gates, then we get an even stronger logic gate, right? And that's the case we can tell with not and. So as he wrote here, not x is just the same as not and xx, and it's actually quite simple. So for x, if it's 0, and for sorry, if it's not x, then it's 0 and there is 1. But if it's not, sorry, not and, my nasty handwriting.
It's actually pretty good. Are you on a mouse?
Yeah.
Yeah, that's pretty good for a mouse.
Thank you. So if it's not and xx, then it's not and 1, 1. We get 0. And if it's not and 0, 0, we get 1. So we can see that these two are the same. Just by repeating the same entry and putting the input into this not and function, we get the same very equivalent truth values for both the system. So actually not and xs is able to express not x. And same for and xy. We can just express it as not and xy, because and is just a negation for because not and is just a negation for and. So not and is the expression for and. And if it's not and, then we have already saw that, we have already seen that not can be expressed by such. We can just replace the thingy to be such, and it expresses the and function again. And for or, it's just not and, not x, not y. Yeah, maybe you can try write it down on the paper and to deliver to derive the truth value. But in the end, you can see that it's like such. These two looks a little bit the same, but they are not the same. You see, in this case, they are the output in the bracket. These two are the same and these two are the same, but this two has to be different for and function. But yeah, so both not all these three different logic gates can be expressed solely by using not and function. So not and function itself has completeness.
Okay.
Yeah.
Because it has all of it inside.
Yeah.
Oh,
But actually, here you can see that lots of other expressions also have completeness. So you can actually try to calculate them out. So maybe I think maybe some computing languages have utilized these different sets of expressions as their basic, but in this case, we only covered not and, so I didn't bother to look at others.
yeah, no, it's fine. Thank you.
Okay. Yeah, so sorry. Did I read this? Combinational logic, present input. Okay.
These are just
yeah.
like,
Hmm?
are these just definitions of?
Yeah, these are just definitions. I think.
Yeah. So I
Yeah,
think
this
it's
is
okay.
when, so this combinational logic is when the output is determined by the present input only, and sequential logic is when the output is determined not only by the present input, but also by the history of the input.
Maybe that's why they use C and S.
Yeah, maybe.
Maybe. Okay.
But it doesn't make sense, right? Because if C is combinational logic, why it suggests the curry? The curry should have considered the history of the input, right? Maybe it's just a coincidence. Who knows?
Mm-hmm.
Yeah. Yeah, here is the definition for completeness. It just means that any logical function with any number of inputs can be realized only by combining a certain set of functions. And in the previous cases, we can see the set of and, or, and not are they together form a complete set. And also not and itself is a complete set. Yeah. Okay. Yeah, and in previous cases, we saw that how the logic is like when there are two outputs as well as when there are three outputs. And here, I didn't bother calculate this because it's too troublesome. But here it just says that when we have n outputs, how it should be like. So when n equals 1, meaning that when we only have one output, then it should be as such. Because when n is 1, we only have one input that we can name it as input x. And if we have an input x, there are two different situations. That is when x has truth value 0 or x has truth value 1. And for this whole thingy here, we can see the output of the function is as such. And when n equals k, that means when we have k inputs, we will have many different possible logic functions because we have two different truth values possible for each input, x1, x2, to xk, right? So in that case, by calculation, I don't know how they calculated that, but in the end, we can have 2 to the power of 2 to the power of k possible logic functions. And the certain, so the i's one, be represented as follows. Yeah. So that's how you derive a specific output for a specific entry. You just derive them. You just replace the thing here and just yeah, that's the thing.
Okay.
Yeah. I hope I explained it well. Do you have any questions?
This was so enlightening. Thank you so much.
Oh my goodness. This is so complicated, I think, especially towards the end. Because I think usually if you are learning them, you have to really try to calculate themselves by yourself on the paper. Otherwise, it's very hard to understand them. But
Yeah.
we didn't do it in the class, as well as we
Yeah, I
didn't.
was
He didn't
surprised.
explain to us what those things mean. Oh my goodness.
Yeah, I was wondering, like, is he going to make us do it on Monday, maybe? Hopefully.